Hey everybody, and welcome to Lightning Talks. Lightning Talks are super fun. This is a short talk format where people can get up and give us a 7-minute presentation on whatever is going on in their world. It's like TikTok, Hackaday for people with long attention spans. So, I mean, relatively long attention spans. So without further ado, I would like to and the slides are all sent to us live. We're going to do this all on the fly. It's going to be slightly seat of the pants, hang on for a bumpy ride. We'd like to start off first with Carl Kosher's Jolly Rancher proliferation. Blatant pandering always works. Come on up, Carl. Thanks a lot.
Hi. So, okay, does this thing work? Yep, perfect. All right. I don't remember what my slides are because I made these last year, but I know roughly what it is. Spacebar, down. Okay. Problem, all MacBooks, at least MacBooks prior to 2015, had this glowing logo on the back, which is friggin' awesome. The other problem was that my school laptop did not. This talk, I'm going to be showing you how I fixed that. So, let's go. On a MacBook, you have the LCD is a, it's a backlit panel with LEDs around the edge, and that has all the diffusers to make a perfectly diffuse, light thing for your backlight. But that also works going the other way out the back of the screen. So if you cut a hole in the back of your screen housing, that light will shine out the back. So if you have a super bright light, you can shine it at a MacBook, and you'll get a kind of vaguely glowing spot in the center of the screen. So, pretty easy, right? You cut a hole in your laptop, you cut a hole in your screen, and then it lights up. So to take it apart, for the XPS specifically, the hinges screw on right here, and the hinges have these strings glued to them, so there's glue around both sides of the LCD, and then you can kind of pull that string out, you can cut all the adhesive, and it peels out. Now, this probably makes 0 sense to any of you who haven't taken one of these apart, so I think I made a picture. So right here, this green here and green over here is glue, and then this string wrapped around the hinges, both sides, and it comes around the edge, so you can just pull, grab on right here and pull it around, and it cuts this glue. So now you can just lift the screen out nice and easily. I completely shattered the first one. So don't do that. So now the next part of the easy process is the guy who runs the University of Washington's machine lab, and he has a water jet cutter. I'm like, hi, can I cut a hole in my laptop? He's like, well, I don't know, why not? So I show up, we put absolute scads of tape on it, have an SVG file of the Jolly Rancher, of course, and cut it out. Looks pretty great. So now you have a hole in your laptop, but you don't want anyone to stab your screen because that would be unfriendly, so let's fill that hole. So I put metal tape in, I pour a mixture of epoxy and then micro balloons so it's, becomes, uniformly opaque. And then right around the edges right here, you can see this kind of weird mesh stuff. This is rubber cement so that the epoxy doesn't get into the anodized layer on the aluminum. So now we did it. This is it, just straight up done. And then I put fiberglass on so that you can't poke it and have it bust out the edge because you only have the epoxy sticking around the edges. The LCD panel is nice. You can see that there is a hole, but they put lightning holes in it instead of just making the whole thing open like that Apple display that I showed you earlier, so I need to cut it. You can see these lines here where you can just cut it, right? So this is another case where I'm going to screw up. I made a Dremel cutoff wheel jig that will let me cut down just a millimeter or two. This is a bit of a Q-tip stuck in here to hold it up off the backlit layer so it doesn't melt itself. Spoiler alert, it melted itself right here because I didn't hold it up far enough. But yeah, you go and make a mess, you spray bits of metal all over your college friend's room because he had a vacuum cleaner and I didn't, so I schlepped it up to his place. And Anyway, that room was a mess anyway, so it wasn't my fault. So now you have a cutout. You have capped on tape around so you don't scratch up your horribly melted backlight layer. And you can kind of see the fiberglass in here as well that's holding everything in. And then now you can see the melting right here. And now the backlight is non-uniform. That's embarrassing, but I have eBay to help me. I found a 4K panel on eBay for super cheap. This is like a $300 option if you buy the thing new, but this had some dead pixels that has gotten significantly worse since. But this time, I just stick pieces of, this green stuff is like a kind of cutting board thing, and I take a knife and just cut there. No melting, nothing gets hot. Everything's perfectly safe because you're only running the knife on top of a cutting board kind of material. And so now you have this beautiful single piece with no bits of metal flying everywhere. And so now you can see it lights up my monitor over here, and then I have the laptop itself. Like that. Any questions? Besides, don't do this at home unless you have a water jet cutter and are smarter than I am about how to cut a hole in your screen.
Marvelous. Beautiful. Oh, how do I get out of here? You think escape? Awesome. Look at that.
And then I've got the web browser opened up down here.
Cool. Next up, we got Davis DeWitt. Thank you, thank you. Following him, Alan Kobayashi. While we're stalling, if you haven't signed up for the SMD challenge, I think there are some slots available still after Lightning Talk. Final round is at 3, though, so I know you got to get in before that.
I just can't get the PDF up. It's on a Google Drive. Like, this is the link that we got here. So, like, that's what we got. And it's a Google Drive link. So I just can't get this PDF without access.
My guess is that it's the Google Drive, or sorry, the Google Drive of whoever was hosting that form, because that's probably where all the files got dumped.
Oh, shit.
I can airdrop it to you.
Yeah?
Yeah, that'd be ideal. Yeah, thank you.
All right, I might run around with the hard drive. Let's see. While we're here, does anyone have a PDF? Is the next one up?
I need him to email it, actually. Airdrop's not going to work. Yeah, it's giving me access denied and all this.
Yeah, that's because the folder's owned by me. Can I just give you access to the folder?
Yeah, I think so, yeah.
Here, let me try that. Here, I'll try my
You
laptop.
probably have a bunch of requests.
Yeah, right. I've gotten them all.
I can airdrop it to you right now.
Okay. That laptop's not signed in to an Apple account. Can you email it? Would that be all right?
Sure.
Yeah. I just tried to enable AirDrop and it wouldn't let me. So it's just super conference, all one word. At hackaday.io. Yeah, and I'll get that open right away. Thank you, man. Yeah, of course. Appreciate it.
Someone's gonna wake up with a lot of emails. Let me in.
Sorry, Bradley, you're right. I have to share this with you.
It's outbox.
There you go. You should be set.
Okay. I might have access.
Yeah.
I've got it. We're good.
Yay, thank you very much. Good call.
Yeah, I mean, brains too for that. I've got it right here, Elliot.
Best ever.
Does the clicker work?
Should do. All right, next up we have Davis DeWitt. Yeah,
Yeah, that'd be cool. There we go. Hello, welcome back. Some of you hopefully saw my talk yesterday because my day job is special and practical effects, but I love lightning talks because I got to talk about the weird stuff that I make that never sees the front of a camera. And so these are the weird projects that I like to build. And last year, if you came to my lightning talk, I figured out how to take jelly packets and make them go really, really fast so they explode on impact. And obviously, you can't just stop there. This was the finished product, the condiment cannon. So I'll talk about that a little bit more later. But I needed a sidearm for it. So if you ever played video games, you have your main weapon. And then, of course, you need something else for if you run out of ammunition, jammunition, if you will, on your main weapon. So if you're not blowing up toast, we need something better. And I was racking my brain. I was like, what object would do really, really well in a magazine? And I was like, oh, yeah, the candy that's made to go inside of a magazine. It's a Pez candy. Which, fun fact, is actually short for Pfefferminz, which is German for peppermint. That's what Pez comes from. So going back to the flywheel design, as you guys are probably familiar with, if you ever played baseball as a kid, it's like the baseball pitching machines. 2 motors that spin really, really fast. In this case, it's brushless drone motors. And so, yeah, pretty high RPM on this one, which is great because the condiments, they kind of lobbed them. It's not super high speed, so I wanted to upgrade that for this project. But I ran into a problem, which is when you spin things really, really fast, they like to rip themselves apart. And so I was using TPU-printed treads, and so if any of you have done like really high-speed projects, you might have run into this before, where you're kind of shredding the material on the outside because it's spinning so fast. So there's 2 options. Option 1, you slow down, which is lame and stupid. So option 2 is you design a bunch of little interlocks into your actual rubber tread, so now when it expands, it's held in place. So you're adding strength to your material without changing your material. And so that's how I was able to get full speed out of the motors so that the rubber wouldn't just like explode out. And this is actually, it's TPU. It's like 75A TPU. So now it would explode off of the wheels at super high RPM. Which was great because now the candy would explode. And that's what I really, really wanted. So this is after it hit. Actually, you can kind of see it leaves like it basically tries to go through the cardboard. It'll dent through the first layer of cardboard and then explode on impact. So we were moving in the right direction. That's a pretty good sign. The next challenge was, all right, how do we get these loaded into a magazine? Because I don't want to use the original Pez dispenser. It's huge, it's kind of chunky, and it doesn't look right. I'm a props guy. It's got to look like it's all part of the same thing. So the only original Pez dispenser component is the spring. And springs are kind of hard to come by if you need a really specific thing. So just gutted my Pez dispenser, pulled the spring out of that, and then made a 3D printed housing for it, 3D printed little magazine. And so this is an earlier prototype, but the finished version actually has a dual carriage. So there's a upper carriage, which goes with the Pez candies, and then the bottom of that spring, because I had to orient the candy vertically, because you don't get a lot of surface area in the normal orientation. And so the more surface area, the more friction, the faster they go, the bigger explosion you get. So anyways, all that to say, I had to extend the magazine in order to get more candy in there. So there's another follower down below with another spring to give you additional capacity. And so the hard part was figuring out, okay, how can I 3D print a really reliable magazine release system and dispenser system? Because it has to get it out of the magazine and into the spinning wheels. So the first idea was a solenoid. That's what the condiment cannon used. But teeny tiny little problem, and that is the solenoids are teeny tiny. And so the return spring on these are super light. And so once it pushed the candy out of the magazine, it stayed stuck in there, because the magazine is applying an upward force from the follower, and so it's holding that solenoid in place. It can't come back out. So new idea, we're going to add some gears to this. So I'm using just a servo with a rack gear. I was racking my brain, as I joked, to come up with this solution. But this was a way to drive the pusher arm into and then pull it back out of the magazine so it doesn't get stuck. And the beautiful thing about this is that obviously a servo is programmable, so this Pez pistol is now semi-automatic and fully automatic. You can hold the trigger and it will release the whole magazine. It will fire it completely in one go. And so after that, a little bit of CAD work to come up with the finished design. Again, it has to follow the design cues of what I did for the or for the condiment cannon, and then a lot of 3D printing, all the different components. And for those of you that do manufacturing, this uses 100 fasteners. Most of those are decorative, But that's the fun part. That's the fun part about making props, is that how it looks is the fun part. How it functions is inevitable. So it has to work. But if it looks good, that's the fun part for me. So this is a small smattering of the parts, custom PCB for the electronics. And it runs 3 batteries. There's a battery here in the grip, and then 2 batteries in series to actually power the motor. So 2 different power sources in order to get as much power into such a small package as possible. And speaking of small packages, wiring these, everything together was a huge pain. This was the hardest part. So there's a bunch of hidden channels cut throughout. You can kind of see it down here, cut throughout the frame. I like it when my builds don't have like wires loose all over the place. I like it to look clean. So doing a bunch of hidden wires and hidden channels throughout the internals of the CAD model so that I could hide everything. It looks nice in the finished product, and then just clamshell it all together in the end and hope it doesn't, you know, explode if I take one screw out. There's 100. I don't have to worry about that. So the kind of cherry on top of this was a transparent OLED for the heads-up display. I've been wanting to use these for a long time. There's like 0 practical applications for these because they're kind of low resolution. They're really, 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 really fragile. I took this to Bay Area Maker Faire. I can't believe it survived, like 5,000 kids and adults and, you know, anyways. But point being, they're really, really cool. They're fully programmable. It's like that same, what is it, like the SSD drivers for typical 128 by 64 OLEDs. Same display, just no back. And so you can do a full heads-up display that's reactive. So there's an ammo counter here at the bottom. You can change your reticle to be different things, battery life up at the top, and then your fire, safe, and fully automatic indicator up on the top. And so the finished product, yeah, a lot of sanding, a lot of painting, if you guys do 3D printing work, in order to get it to look weathered, as I talk about in my other props work. Everything that exists in this world has some sort of wear and tear, so you have to replicate that so that it looks, you know, it looks the part. Pretty much everything's 3D printed with the exception of, for the finished version, the actual middle barrel is CNC machine, just because I'm tapping a lot of screws, so that I don't have to worry about stripping anything out. And that's the finished product. So did a little bit of speed tests, and it's roughly 65 miles an hour barrel velocity, which is pretty good considering, you know, these are really small batteries, and I'm trying to launch something that is not super aerodynamic. But they explode on impact either way, which is really, really fun. And so now it's part of the food fight collection, as I like to say. And that's the Pez pistol, everyone. Thank you guys so much. Appreciate it.
Perfect. Thank you. Give me the clicker. The clicker. Thank you. Lovely. The food fight collection. Here you go. Do you want to do? It's the last one.
Okay.
Yeah, I think I highlighted it for you.
This one here? Okay.
I think so. Then without further ado, welcome Alan Kobayashi to talk about Star Trek display tech in 5 minutes.
Hi, everyone. Oops. So this is the. I tell you what, hold on to this. Give it to me at the very end, and you'll know why. Hi, everyone. This presentation, which I had planned to do a couple weeks ago, fits in perfectly with the stuff yesterday with Michael and that group, because the technology we're talking about here is Star Trek: The Next Generation, Patrick Stewart, and of which there was no, at the time, video playback was, especially on the budget of a TV show, just wasn't going to happen. And also there were no wide format inkjet printers to make backlit. Basically, the blacks were just not black enough, and you'll see why when I go on through these. So this is the technology that Mike used, and also from yesterday I learned that it got used during the motion picture as well. So, yeah, all right. So it starts with photostat cameras, which is a mechanical system that used a photo processing, a photo film from Kodak, Kodalith, which some of you may know, very high contrast, clear or black, and that's basically it. They use it to create half-tone plates and everything. There happened to be a company called Continental Graphics on La Brea Street, so it's about 6 blocks away from Paramount, and they do stat camera work for magazines, newspapers, turning things into halftones, so you can create 4-color art, but not, full thing. And so stat cameras can be really huge, but you put the artwork on the plate over on the right, and then you expose the film, and what you end up with is this. Well, let me just back up just a little bit. This camera creates the film media, which turns into this, except this is after you add the color layers. And those color layers are these on the back. So what you get is the black, transparent black areas, and what you have here are film gels, just Roscoe gel material, layered and applied behind certain areas in the color and stuff, and you can see where certain areas have certain colors, and that's just certain gel material. And then finally, over the whole thing goes a tracing paper, diffusion light, gel lighting or something. No electronics involved, no inkjet printers or anything. And this is sort of the summary of it. Black and white artwork, like there on a board, just like you people might have seen way, way, way back in the day if you worked on newspapers and print shops. Put it through the stat camera over there in the middle, and you end up, can you see the clear areas? I peeled back all the gels and the diffusion material, and you can see it's clear. But the blacks are extremely black. You could actually, not recommending it, but you could hold up to the sun and not hurt your eyes. You get a teeny tiny white dot where the sun is, but it's that dense. And you can see this came out of yesterday's talk. You can see the gels. You put them together and they create different tones. But again, this is completely mechanical, so to speak, photographic. There's no electronics involved or anything like that. It's all photographic process. And so I'm going to show you an example of how it gets used. This was an episode from 6th season, I think episode 9. Lessons. The captain falls in love over a piano, if you recall the episode, and gets to play his flute, the Ricecan flute. I hope I pronounced that right. So this is the Ob's Lounge that we've seen a million times. Watch out for that graphic in the upper right corner. There's 2 of these monitor screens at either end of the Ob's Lounge. That graphic should look pretty familiar. It's the same one we just saw. And if you remember what we saw, it's the same graphic now lit from the back. And you can see the blacks are intense, no light leak, it's not gray or anything, which is what you get with inkjet nowadays, even with really good quality. And you can see the light comes through and the transparency and everything. It's just the intensity of the colors just can't be matched even by today's standards without spending colossal amounts of money. And this is done on television budget. So these got changed out all the time. Let's see. Another beautiful example, and this is from our friend, Mr. Doug Drexler, who worked on DS9. It's a warp subspace field. No, what is it? It's across the bottom. It's Bajoran subspace forgive me, Doug, warp conduit. But you can see the colors and the intensities, but the little gradations, it's doubling up on, well, the purple color. 2 layers of it creates a darker image. But again, the intensity and the tonalities and the subtleties you can get is just really well done. So give you an idea of, remember, this is all the late 90s. Inkjet printers still yet were not quite up to snuff, making blacks, especially at a lower cost. Then, a couple years later, I went to work for another space fleet. Very lucky to work for Babylon 5, and this was 96. Lessons came out in 1993. It was 6th season of Next Generation, not the last, 7th. But then I went to work for Earth Alliance, and it was a direct technology transfer. There was a spaceship, third season, I think, called the Thunderbolt. The Star Fury is the one, the beautiful ship that can rotate on its circles, but the Thunderbolt was meant to be like a bomber in the atmosphere. So that's what you have here. And so there was a cockpit inside. So you can see the graphics I did right there at the top. And here's a closer shot. This is the Rio, the behind the pilot, but you can see it's the same technology. Black film negatives with gelling. Am I getting 2 minutes? Okay. And those images are dye sublimation prints that we happen to have a dye sub printer, so I could print transparencies. So that's why they're kind of continuous gradations, but everything else is film gel, just like the next generation. The palette is completely different. This is Babylon 5. John Iacovelli had picked this palette at the production center, but the technology is exactly the same. By the way, you don't see that view ever in the show because post-production kept putting in their own version of a dashboard. That was just to cast light on the actor, and just in case they ever shot that direction, it wouldn't be a big blank there. So, War Room console, same technology. Palettes completely different than Star Trek, but the same technology. Film gels, 96, and this is the med lab. Same idea, you can see it, and now that you can see it, right? Anyway, and this is my family on Star Trek. It's Michael Okuda, Denise, Ben Betts, our video operator, someone up in the left corner, photobombing, Eric Roberts, Jim Vanover, Jeff Mendel over there on the far right, the par excellence graphic designer, Eric and Jim, those two are part of the video playback crew. So that's, oh, there's me fixing something. I have no idea what I'm fixing. I think this was TNG, this was some, yeah, it's not the warp core, so it's something else. And that's all. Except
the big secret reveal.
yes, I have the graphic, the Brisalis. Oh, I have the Brisalis graphic with me. I happen to possess it, and so well, we don't have a backlight, but there, and you can see the back. So don't want to interrupt the flow here, but I am going to make myself available at the end outside somewhere at a table, and people can look at it and paw at it and whatever they want to do. Okay? Thank you. Thank you.
Thanks very much. Oh, that's actually really cool. You can see the little patches that make the darker spots. That's actually awesome.
That's another talk about polar motion.
Nice work.
Completely different talk. But another
Dave Cox. He's right. Oh no, it's the Gephards next, right? Here. Hold on.
Yeah, I got you.
They have a link.
Take my notes.
Sorry. Yes, that you emailed it over, right? Yep. Andy. Yep.
Thank you. You have too many SAOs. You need to display them somehow. This is the brand new hotness. This is the new solution. This is SAO Affinity. I hope I'm not overselling it. Please welcome the Gephards.
All right. Too kind, Elliot. Thank you. Yes, so this is a lighting talk. Is that what this is? Or is it a lightning? Well, it's to be a little bit of both. Thank you for that. Yes. Yeah, you're on to us. All right, so raise of hands. Who has a whole bunch of SAOs sitting in a drawer or a box, and they're not being displayed as the awesome art that they are? Okay. This is our attempt to solve that problem. And Ben, are you here? There he is. Inspiration, I believe, was planted in my mind. He came up with a really cool hexagonal design. It was on Hackaday. You guys all seen it? There it is. Check it out. Okay. So that was percolating in my mind. I'm like, it's cool. I want to be a little more modular. And that's where this was born. I think this inspiration completely, it was percolating in my mind, and then it struck during a conversation with a coworker who was talking to me, and I wasn't really paying attention, and I started sketching the idea. But that's, you can't control an inspiration strike. So that night, catted up the first version, and the idea is this ultra module, or ultra, modular design. You could 3D print and just get an SAO connector, and then solder in a piece of perf board or a proto board on the back side, wire it up. So super cheap, super accessible. Anybody with a printer could do it. 1.5 inches by 1.5 inches. Yeah, that actually really kind of stunk. So talking with my brother Andy, he's like, it needs a circuit board to make it easy. Wouldn't be required, but it'd be a nice accessory. So lots of late night phone conversations and video chats. We iterated and came up with a little easier way to do it, and you're going to talk about that now.
So we didn't prepare. In the spirit of a lightning talk, here we are. And we just have our photos that are up here on the Hackaday.io page. I was trying to find one with the circuit board in the background. But the point is, there's a circuit board behind each one, and then there's a 7-pin connector that goes between each one. So you can arrange these however you want. This just happens to be a grid to try to fit it, There you go. And the 6 pins are the standard SAO, and the 7th pin is for a serially addressable LED that's on each board. So I think you can maybe make that out. There's an LED strip that's also in the background here that's dynamic. And that one is controlled through one of the GPIOs of this grid tile up here with... Oh, I know a guy. Exactly. Yeah, I appreciate that you appreciate that. I was like, oh, you don't see many of these around, so... basically, it controls the whole entire array through the way that you wire these up, and there's some little solder jumpers underneath there. I don't know if you can, well, they're under the resistor, and these solder jumpers configure how you do that serial addressing from one to the other and all around. So it's been a lot of fun, and it is definitely a nod to Gridfinity by Zach Friedman. I don't know if you guys know about that, but okay, good. 42 millimeters.
Yeah, sorry, I forgot, because we're totally unprepared, but it was 1.5 inches by 1.5 inches, just I kind of chose that, it felt right, and quickly my brother pointed out that that's really close to 42 millimeters, and it named itself, so shout out to Zach there. And then I also forgot to mention there's bow ties that hold everything together, and little edge plugs to clean up the edges. There's holes between each section to run wires if you were just going to manually wire it up without a circuit board. We made some hinges, so come up with a basic design, and I think the community's creativity is going to go crazy with this.
Yeah. So find us outside. We've got a bunch of these kits available if you guys want to try them out and riff on it and inform us what you think is good and bad, and we'll iterate to the next version. That's it.
Thank you.
Thanks very much. It's a great idea. That's a problem we all have. Real problem. Real problems really solved. Next up's going to be Dave Cox. Come on up. We will load your slides as soon as we can mouse around and find them. If you can't tell, I'm not a Mac guy. So embarrassing. Spacebar or the clicky, whichever you want. There you go. Good enough. All right, ladies and gentlemen, Dave Cox, Hacking the Broken, one cold solder joint at a time.
Woo! Too many things. I am Dave Cox. I'm an engine nerd, just in case. What I am here to talk to you guys about today is basically the repair movement, which is volunteer-based. It's all about people like us getting out there and helping people fix stuff. Now, being that I'm one of those detail-oriented people, I actually put like every word in here, so I'm going to start reading this now instead of improvising. So I think of Supercon as a celebration of making, hacking, recreating, but there's an adjacency that I'd like to address, and that is fixing. Repair is as old as making. It used to be a valued skill, but nowadays with very cheap materials like plastics, very, very cheap labor, so many times things are just, it's easier to justify throwing it out than fixing it, right? And especially with products designed for manufacture and planned obsolescence, not for repair, there is no shortage of broken things. Things. Broken or not, but things. So I want to talk to you about this movement that's been gaining momentum for a while now, and a place where your particular brand of nerdery is desperately needed. A buddy of mine and I did a repair thing out of our dorm room back in the 80s, but I kind of lost my way in the corporate world for a while, let us say. Then a while back, I was driving past the library, out of the corner of my eye, I see they have one of those vinyl signs out front, and I see something about fix your stuff, and I'm like, whoa, I want to be a part of this. So I turn around, I go back, and I am disappointed to realize that the sign says, if you cannot fix your stuff, we have an e-waste event. And I'm like, okay, so we probably can do something about this. So I have some friends at a collaborative art place in San Diego called Collab, and I proposed, well, hey, could we do like a gathering of people offering to do repair stuff, advertise it, kind of not just fixing, but teaching people about fixing. She said, sure, so I drafted some of my friends, including this guy here, and we got together, and we fixed, oh geez, there were solar lights with broken wires, a bunch of things with dead batteries, as you all know, batteries that are very dead can cause other problems. Let's see, a chair that was split, blinkies with a dead charger, broken zipper, all sorts of things like that, connectors, power supplies, blah, blah, blah. Anyways, we ended up fixing about 3/4 of the stuff. Not 100%, but we didn't go with all the parts and custom bits and so on and so forth. It becomes kind of a part of the relationship to fix a thing. Go to Amazon, go to Alibaba, whatever, try to find this thing. Bring it back. We'll fix it another time. And bottom line, it was so satisfying. At the end of the day, one of the folks turned out to be the lead of the San Diego Fix-It Clinic, volunteer organization which has been doing free repair events at libraries and community spaces. That's when I discovered this whole community that actually had the same idea. And they'd already done a lot of the homework, so why not jump on their bandwagon, right? A volunteer-based repair cafe movement. It's attributed to a woman named Martine Postma in the Netherlands, started back in 2009. It shares a lot of DNA from the world that we love. The hacker, nerd space, the ethos of make, and the culture of curiosity that defines Hackaday. You've heard of iFixit, undoubtedly the cool soldering iron people, so on and so forth. They're actually out of San Luis Obispo, which is my second home, and they have up in that area something called the 5 Cities Repair Cafe. They've hosted some of the events out of their space, and you know, they share the same spirit. If something's broken, you open it up, you diagnose it, you fix it, and you share what knowledge you've learned. So that's where you guys come in. You could be a fixer. The folks attending repair cafes bring in all kinds of things, blenders, bar stools, pants, egg incubators, lamps, laptops, but often the most important thing isn't so much the thing itself. It's the old stereo that was their father's, or a lamp that sat on grandma's bedstead. A teddy bear with a torn seam. We get a lot of repairs from seniors. We do some things at senior centers, and the classic is, you know, this 87-year-old lady brings in this alarm clock that her husband gave her on their 25th wedding anniversary, and how much emotional value that is in that thing. So many times you can help mend both things, keeping the thing out of the landfill, imparting knowledge, and empowering people while also helping them reconnect with an object they thought was gone forever. So my call to action is simple. Go find a repair cafe near you, check it out, see if it's something you can help with. Or if there isn't one, you can get, where was I going? You can get together with some of your friends and start your own. The first repair cafe was just a few friends trying to help out and fix stuff for free at a coffee shop. There is a, oh, I skipped a section. There's an emotional and even animalistic, or animistic, not animalistic, that's another thing, animistic quality we ascribe to some objects. They're not just devices, they're faithful servants. They fit in your hand a certain way, or they fit in your house. You have a relationship with them, and they hold a memory. There's this Japanese art, kintsugi, where the cracks in a broken bowl are gilded with gold to celebrate the history of the object, not hide it. You all have unique skills, many of which could help mend both things, keeping them out of the landfill, and imparting knowledge, empowering people, while also helping them reconnect with that object they thought was gone forever. Another phrase is from the Jewish tradition. There's something called tikkun olam, which means to repair the world, one small step at a time. That's what you're doing every day. Every time you solder a broken junction, sew a seam, or glue a crack, you're not just fixing a thing. You're doing a small, tangible act of mending our relationship with technology and with our planet. We need your clever hands and your curious minds. Thank you. Here are a couple of resource slides. Thanks. Here are a couple of resource slides. Whoop, what did I do? I went backwards. How do I bring this up again?
Yeah, just put them up on the screen.
So, yeah, California-based sort of stuff. Ones that I'm most familiar with are the San Diego, the 5 cities. There is also one in LA. I didn't get that on here. Oh, Glendale, I guess, yeah, that one. And then, of course, internationally from lots of different spaces.
We have repair cafes in Germany. Check it out, repaircafe.us if you're local. Thanks very much. Next up, we've got Justin Miller. Come on up. Oh, yeah, okay.
Cool.
Clicker if you want it.
I'll just do here. Cool. Hey, Supercon. I wanted to share a fun build I made a couple years ago. Officially, it's called Catch the Wave, but I submit to you using, abusing microcontrollers, Chromebooks, and electromagnetism for science education, fun, and no profit. Like all of us, I could probably skip this. I like to mess in a bunch of different media, software, traditionally, a lot of hardware, building, lumber. So I wanted to turn my efforts towards kind of making something that you'd find in a really fun science museum for kids. And I did this for a local, I'm in Portland, Oregon, for the OMSI Museum Science Festival as a way to kind of give back to the community. So it's called Catch the Wave, and it's a series of 4 learning stations where you sit down and learn about how electromagnetism relates to speakers, microphones, and recorded and played back audio. This is what it looked like at a Girl Scout STEM fair a couple years ago. Maybe you remember from elementary school, you know, if you apply a current through a coil of insulated wire wrapped around a core, you magnetize the core. You can do this selectively. Maybe we've heard that, maybe we haven't. Maybe you also may know that this is the basis of how a speaker or microphone works. You can translate in either direction. When you magnetize the coil in a particular direction with the current, it can repel or attract to a permanent magnet. We move a paper cone, we generate audio. Similarly, a microphone moves the paper cone and records the audio. So this is super relatable for kids. Because even with smartphones and tablets, they know that there's a microphone and a speaker. It doesn't look the same as the big old, you know, speaker in a speaker cabinet. But to see this manifested physically in a way that they can touch is really relatable. So the first station looks something like this. You've got a screen up top, electromagnets mounted on the green thing in the middle. When you apply current, you know, you can get the magnet or the compass to snap into place pointing at the electromagnet. You also notice the graph. It shows a 1 when the current's applied and 0 when it's there's no current. And you can get paper clips to stick. I mean, this is jaw-dropping for kids and even adults to see the paper clip stick and then fall off again when you release the button. Yeah, I mean, literally jaw-dropping. It's really fun to watch. So the second station kind of builds on this. What if you change the current direction? I 3D printed a little swing with a magnet on it, electromagnet underneath the swing. You change the direction of the current, you repel the little swing and get the swing moving back and forth when they move the switch. And so you can start to see how translation of current relates to physical motion. And so now the graph goes in the positive and the negative direction. And then building from there, what if you could flip that switch hundreds or thousands of times per second? If you could vibrate a piece of paper, say the way a bee's or a fly's wings vibrate, that's in a sensitivity range that moves the air in a way that your eardrum can sense, and we perceive that as sound. So imagine vibrating or changing the switch direction 440 times a second or 800 times a second. So this is a paper cone speaker that I encourage kids to touch while they're playing with this, and then they can crank on the frequency and get sort of a relative display. You can see the graph kind of condense or expand. It's not pixel accurate, but it gets the idea. And you can see how electromagnetism translates into sound and even something that you can feel. And kids relate to this too with subwoofers and low sounds and how that's enough to move the water in your body to where you can feel it. And then the fourth station is just a speaker and a microphone, kind of abstracting this to the next level in the middle. And you can record and play back your voice with pitch changing and the chipmunk voice and reversing it and things like that. And so it kind of talks about the idea that you can record these signals as ones and zeros or ranges of numbers and then change those and play those back and affect the way that the sound comes out. Kids love this. Most of the shots I have of them really having fun are, of course, at the orange station because of the chipmunk voice and changing your own voice. But these are shots from the Science Festival a couple years ago from when I built the thing. And this is from a Girl Scout STEM Day as well. So a little bit about the build process. This was my prototype version. It's sort of, the idea was, okay, I'll make this little durable box thing with a screen in the back, and then the front will be kind of the playground workspace. And the magic trick here is that they're actually Chromebooks that I built a cabinet around and didn't even use the keyboard, and then made a little compartment in the front where you put the microcontroller and the guts of the rotary encoders and that sort of thing. I like to call this business up front, QWERTY in the back. Why Chromebooks, though? So I've got mixed feelings about Google in education, but Chromebooks are cheap, durable, and obtainium. So I got these 4 Chromebooks for $50 a piece on a site called backmarket.com. Super easy to hack the firmware. I say that. Super easy to hack the firmware and install Linux on, and thus you can drive microcontrollers over USB serial and drive displays. They're durable. I like I read a statistic that most Chromebooks are meant to be dropped from 3 feet onto concrete and have a soda dumped into the keyboard. So, they hold up. And there's touchscreen potential too. I played around with that a bit. So I used Pygame for the framework on this. So the application running on the machine is Python based. And Pygame sees touch input on touch capable devices the same as a mouse event, so it's super easy to program and do stuff. But ultimately, I wanted to get away from touch screens and kind of the traditional view of things. That's why I hid the keyboard. And so, yes, they can touch the screen, but it doesn't do anything. It can kind of bang on it. Yeah, so I did a lot of repetitive cutting with my table saw to build these little cabinets. And you can see on the right side, this is the thing that sort of slots over the top end of the laptop and slides down and then locks into place. Pick some real pretty colors that draw you in and are appealing to the eye. And then built, this is like the prototype version with the swing, so just the 2 LEDs stuck in here to kind of test it out. But this is an H-bridge that would drive the electromagnet, so I did that for the first 2 stations. So like I mentioned, it fits in the business part in the front. And then this is a little hack I was kind of proud of. Because I have to take these apart and disassemble them at the end of the day and stuff like that. The USB connection coming from the microcontroller comes over to the left side of the cabinet and then out this little slot. And you plug that into the side of the Chromebook, and it also locks the whole system together because you can't then pull the Chromebook. You can see the screen sticking up in the back there before I put the sheath on. It kind of holds everything together, and then I've also got the ability to lock the top on with a hasp and hasp and a little lock. I didn't ever have to do that. These were generally attended displays, and I was there, and sometimes some helpers. And I made handouts to go with this, which was good just to kind of orient to the thing, as well as, for the most part, this was me doing this at the science festivals, and occasionally they get swamped with kids. And so this is a little bit of an assist to the parents with them as well, to kind of share the load on the educational process here. So again, why? Yeah, I'm not usually involved in education. I don't even have kids of my own. I don't generally do a lot of stuff. Yeah, I enjoy kids. I like my nieces and nephews a lot. But I like learning. I like sharing learning. And I thought this was a great way to see where designs hit the pavement. In particular, kids, as we all know, are rough on things. And it was fun to kind of see, oh, yeah, I'm going to build this, and it's going to be super durable, and see where that failed and learn from it. And that's kind of what I wanted to do. The goal of this was, like I said, building sort of what I thought of as a fun science museum caliber exhibit, or attempting to, and then learning a bit more about how to make things durable. And yeah, I did this because I could, and I wanted to give back, and it's been really fun and rewarding to, that's why I mentioned the no profit part. It's just, I spent a lot of time kind of carting this around for kids, and it's easy to set up and do, and everybody, kids and adults love it, and I've really enjoyed it. So thanks, that's my talk.
Thank you very much. Next up, we've got Marble. Come on up. Can I unplug the HDMI cable? Is that a problem back there? Video peeps?
Should be okay, Elliot. We've done it.
Forgiveness, not permission. Exactly.
Okay, cool. What's up? Nice.
There you go. Without further ado, please welcome Marble.
Hi, thanks. My name is Marble. This is all very last minute, so I have no slides. I'm an embedded engineer, and I love working with KiCad. I want to do this a little bit interactive, and maybe show of hands, who here has worked with KiCad or works with KiCad? That's a lot of people. Okay. Who here has worked with CMake, or not CMake, Make, GNU Make? Okay, maybe same amount. I like things automated, and I thought, yeah, how can I automate KiCad? And the first idea was, okay, let's add a Makefile. And what I want to show you in this talk is just this little repository I've been working on over a couple of years now. And the nice thing is with like KiCad 7 or 8, we got like the CLI. And this helps us output all of our build files just from the command line without even opening KiCad. And in this repo, next to like some sample source files, template source files, there also is a Makefile, which just lists like plots, renders, Gerber, zip files, and everything as targets. And it even uses Make to like make smart decisions about what to build again. Like if you didn't update your schematic, you don't need to update your schematic plots and everything. So yeah, that's like the start of it. And next question, who here has used Nix before? Well, okay, fewer people. Let me say this, if you like Ansible, you will love Nix. And if you hate Docker, you will love Nix. And in Linux, the philosophy is everything is a file. In Nix, the philosophy is like, yeah, everything actually is an expression. And an expression you can like resolve in a functional manner. And so Nix also has like Nix OS, which is a Linux operating system built on that philosophy, using Nix as a package manager. And one nice thing about this is Nix gives you one nice tool called the Nix shell. And this is comparable to like a Python virtual environment. In Python, you would say something like virtual environment instantiate and then activate it, and then you can install packages. Nix provides this, but not just for Python packages, but for everything. So the next step was to add a shell.nix file to this repository. If you're not familiar with Nix, don't be scared by this. Essentially, up here, I just say I want to build from a specific revision of the package repository, and down here I say, yeah, please make a shell containing like KiCad and all the utils I need to build this. And what I then can do is, one second, I can go into a shell, and what I did up here was say Nix shell, and this essentially enters the environment with all the tools required. It also builds KiCad if necessary, it installs it and makes it available like in your path. If you're familiar with Nix, you may know this may take a very long time the first time you do it, because it has, if necessary, to download all the binaries and packages and everything and install it, but if it's in your cache, it's really fast. And then what you can do is simply say make in my template repository, and this will build all the outputs regarding to your project. I would just like, cancel this. Yeah. That's all nice, but Nix has like another actually very core feature, which is building packages. So I thought maybe I can just treat my hardware project as a package, and you actually can do that. I added a default.nix to my repository. If you're familiar with Nix, you know that you can then simply say in the repository Nix build, and it builds the package. Like normally you have packages for software or for libraries, which you can build with this. But if you treat your hardware KiCad source files as just normal source files, KiCad as like a compiler, and the outputs as like the binary, you can also just say, okay, build a Nix package with all my stuff. And one second. Oh, I have to zoom in a bit. Like this is the template repository, and if you say Nix build, you will get one of those results folders, which is actually just a symlink into the store. And here are all the files you would need to produce your project, like the zip file of your Gerbers, your BOM files as a CSV file, even renders, like KiCad now implemented rendering from command line, which is pretty nice. And the next nice thing you can do is you can even say, okay, I don't even want to build on my computer, because GitHub has integrated Nix into their CI pipeline. In theory, this project should have like a green check mark, but I think GitHub at some point garbage collected it. But here in the workflows, I simply added a build YAML file, which then just calls like Nix, says, okay, with Nix, please build this package. And then in the background, GitHub builds KiCad, which then is used to create all the output files, and that they then get uploaded to like sorry, forgot the word, to the artifacts, and you can even like make releases with those, and also in theory run ERC and DRC in the pipeline, so you can check that your files like didn't degrade in quality. And yeah, a sample project, which is a project which isn't just an empty sample project, is like a chubby head I was working on. Like it's shelved currently, but yeah, it's based on like the reverse engineering work, like really great work done by a lot of people. About the color light, and it's like a head you put onto the board, which turns this LED driver board into an FPGA development board. Also need to zoom in again, sorry. And yeah, and here, like I did run make, and then you can, for example, go into the exports folder, and for example, look at the renderings, and you have like the bottom rendering, which is created automatically, like you can see the date is today. I did this earlier, and or the top view and stuff like that. And yeah, that's just what I wanted to show you. If you're interested, my handle on GitHub currently is cybermurmel, and the project is called KiCad template. And yeah, thank you for your time.
Thank you. Could have used that a few months ago. Thank you very much. next up, we've got Alex Probst. Come on over. We'll set your slides up. 140 watt USB PD.
All right. Thank you, everyone, for having me up here. I'm Alec Probst. I'm an engineer at Qualcomm. I know. Don't ask me about Arduino. I didn't know anything either until you guys heard it. So you can ask me later, but I don't have anything that I can tell you about it. But I'm not here to talk about that and my day job. I'm actually here to talk about Stamp PD. This is a stamp that allows you to request 140 watts of USB power delivery. So Stamp PD is kind of a project I've been working on in the background in my free time. And my goal was that I wanted to stop having to recreate USB power delivery every time I wanted to make a new PCB design. It wasn't my focus on a lot of the PCB designs I was doing, and yet I was spending time having to recreate the same thing again and again. So I had heard about solder parties RP2040 stamp and was really inspired by that because you could just drop in an RP2040 and not have to re-implement all the hardware that was going along with that. And I also heard about Pico PD, which is on Hackaday.io, which implements a USB PD stamp into a whole USB Pico PD. And so that lets you get all this power into this nice form factor pretty easily. So what I've done here is I created this 30 millimeter by 30 millimeter stamp, which allows you to connect a USB-C port through the pins on the side that you can hand solder, and then outputs on the top and bottom whatever your requested voltage or current that you want. And so, if we go to the next slide here, we can actually communicate with this stamp through I2C, which allows you to use almost any microcontroller that you want. So you're not locked in to any specific decisions. You can have variable voltage and current selection. So you have the standard power range of fixed voltage and currents, and then you have some of the EPR, the extended power range, that you can actually select from here. And so you can select the fixed ones that are available from you for 5 volts up to 28 volts. But then you can also actually have variable voltage between these steps of different amounts. So don't fully take this graphic. This is not representative of what my Stamp PD can do. But you can actually do 100 millivolt increments between the SPR range and then 200 millivolt increments between the extended power range, all the way up to that 140 watts that I was talking about. With this, I also added in 2 dedicated buck converters for 5 volts and 3.3 volts. So that way you can power any microcontroller you want without having to worry about what your actual requested voltage is. So you can connect the dedicated buck converter lines, which are 2 amps each, or up to 2 amps each. And then you can also connect whatever mixed voltage or variable voltage you want with that in the stamp. This also has a built-in back-to-back NMOS converter, or protection, and there's automatic user-adjustable power, so you can enable or disable the power as you want through I2C, with safety features built into the controller for over temperature, over current, over voltage, under voltage, and moisture detection. And like I said before, it is 30 millimeter by 30 millimeter, but I haven't actually gotten the prototype back yet, so we're gonna see if it melts first thing, and then I might have to make it a little bit bigger if we end up having 140 watts being too big and too much power. So that's pretty much it. I have some next steps right now, which is I'm in the very final stages of the routing, which you saw on that first slide. It's a 4-layer board. The main controller is an AP33772S by Diodes. I like the chip for the most part. The documentation's pretty decent, but there is some missing stuff in there that you can find on the Hackaday link where I've talked about it. I need to order the prototypes. They've actually been designed around the JLC PCBA service. So that way I can just kind of order, or anyone else can just kind of order one that's fully assembled and ready to go. And then I do need to actually test these, obviously. And Frameworks actually has a new 240 watt power supply that they've come out with, which fully supports all the variable voltage and current for the USB PD 3.2 spec. So I plan when this comes in the mail, I was hoping they might have some here, but they didn't. When it comes in the mail, hopefully this month, I'll actually be able to plug this in and do a full test and make sure that it doesn't melt in your hands. All right, so you can find everything that I just talked about on Hackaday.io at 203747 stamp PD. The design logs, files, and updates are going to all be posted to there. There's no Gerbers, step, schematics, or BOM yet. I'm still finishing the design up, so once that's done, I will be uploading those, so you guys will be able to access that. And then it's possible I'll do a Tindy sale, but I have yet to decide if I want to actually dedicate a lot of my time to making a bunch of these to do that. So if nothing else, because it's JLC PCBA, you will be able to submit them yourself for them to be made for you, if nothing else. So that's the plan. And that's Stamp PD.
Thanks very much. Next up, one Alex follows the other. We've got Alex Whitmore. Woo! Slides coming right up. Sweet.
Hey, y'all. So first thing, while he gets the slides up, how many of you 3D print? Cool. How many of you store your filament in vacuum bags so that it stays dry and doesn't get wet? Okay. Of the 7 of you who raise your hands, how many of you do that for PETG? Of all of you, you've either learned one of two things. One, you either think PETG is terrible, or two, I guess I asked about PETG, whatever. The rest of you who don't do it with PETG have learned that PLA is really forgiving. And I am about to tell you why as soon as these slides are up. No worries.
Here you go.
Cool. Yeah, okay. So, psychrometry, humidity. So, a lot of you, it sounds like, already know, but for those of you who don't, polymers like we 3D print are hygroscopic. They absorb moisture from the air, some more than others. So, some, like PLA, are really forgiving. Some are not. So, PETG, nylons, they all absorb a lot of moisture from the air, and you basically can't print them if they're wet. They bubble, they ooze, they have bad layer adhesion, they have all sorts of problems, they crumble. So this is what my filament storage looks like. I have a bunch of dry bags on one side, like on a rack, for filaments that I care less about, ironically. I have a Rubbermaid tub full of PLA and a ton of desiccant at the bottom. And that's how I kept my filament dry, until I realized one day it wasn't. So one day I went out to my garage and I saw this. I was sick at the time, so I had like a week of not much energy to hang out at home and do projects. I noticed that my humidity indicators in one set of my bags were bone dry and the other ones were like ambient humidity. And I thought I had broken bags. And immediately what happened is I remembered stasher bags that I'd used in the fridge. I don't know if any of you used these before, but I stored avocados in them and they would dry out after like a day or two. And in the process, I found out that silicone is incredibly transparent to humidity. Like humidity just goes straight through silicone. It, might as well be a window for water vapor. So I did some A/B testing with my vacuum bags and learned that all of the vacuum bags perform identically. I had some broken humidity indicator cards that were stuck on dry, and it turns out these PET vacuum bags are also basically transparent to humidity. They don't do shit for storing your filament dry. So to baseline that assumption, figure it out, how many of you have ordered FPGAs and they came in these like really nice, thick, metallized moisture barrier bags? Well, they're called moisture barrier bags for a reason, because they actually block moisture. So I put some desiccant and hygrometers in a moisture barrier bag that I got online and some in my PET bags. And lo and behold, it's a bit of an eye chart, but The yellow trace is the PET bag, and the blue trace is the moisture barrier bag. And we can see already after like a couple of hours in there, the moisture barrier bag is getting drier. And then after like 2-3 weeks, no, this was, yeah, 2 weeks, lo and behold, the PET bag just leaks moisture like a sieve, and it was basically back up to average ambient humidity in like 12 days. So then I did an experiment. I tested with a few other kinds of bags. The stasher bag, which I already knew was bad for this. An ESD, a regular ESD bag, so still a PET bag, but like lightly metallized for ESD reasons. And then just a regular Ziploc. The stasher bag is a joke. And then the other two also, you know, don't do a great job blocking moisture. So then I finally did a longer term experiment where I put a couple of these bags. I was trying to test the efficacy of activated alumina versus regular silica desiccant. Slice Engineering says that activated alumina is 1,000 times better than silica, but actually weight by weight, they're pretty much identical. Silica is actually a little better. Volume by volume, activated alumina is better, but it's also heavier, so it doesn't really make a difference. What does make a huge difference is use the moisture barrier bags. Annoyingly, they're like $1 a piece instead of very cheap, but vacuuming out the bag doesn't do crap. Turns out the amount of air enclosed in the bag when you first put a filament spool in there is only about like 0.15%. If it's really humid out, it's like 0.15% of the amount of moisture required to saturate a kilogram of filament. So vacuuming it out doesn't do anything. Putting it in the right bag does. And also, going back to the first slide, that Rubbermaid bin that can fit a ton of silica desiccant to the bottom, it's actually kind of the best thing you can do. It's sort of the easiest. It holds 8 spools, and that thing goes for months without breaching 20% humidity without having to change the desiccant. So yeah, don't use vacuum bags. They're literally useless for this task. That's it.
Thank you very much. Today I learned. John, he said his slides, he saw them up here. See if we can find them. Yeah. Secret emails. Oh, no worries. I guess in the meantime, I should say, we are actually running a little bit late. If you guys want to stick around, lunch is easy to pick up out there. So I would stick for lightning talks and just pick up lunch on the fly. We're probably going to go 15 minutes over is my guess. Enjoy. Bonus lightning talks. Thank you. And with that, John Abbott.
So spacebar? Spacebar for slides? Okay. So I'm a baker. Not by profession. I'm a burned out IT guy by profession. But I enjoy baking. And I like really good bread. And I live in northern Minnesota, the land of $4 bread. So I built an oven in my spare time, and now there's lots of good bread. But I am an IT guy, and I've done some carpentry work, but step one, learn stonemasonry. Okay, so that's kind of what this whole project has been about. It's been a lot of learning. And I'm an IT guy, so I had to build in some sensors. So in the structure of this whole thing, I have embedded thermocouples inside of glass tubes. So that, 30 years from now, if the thermocouple goes bad, you just slide the old one out and slide a new one right in. And then this process started. You all know about this process. So reading the data from these thermocouples, and I eventually settled on this design, which I thought was beautiful, elegant, very nice. I was paying for this, the thermocouple amplifier, I was paying about $18 a piece. And so I didn't want to put in 12 of them, which is how many thermocouples I've got. So what I did is I used a multiplexer in there so that I could read each thermocouple independently. And I thought this was a great idea if it would have worked, but it didn't work. So what happens is I would get about 50% readings and about 50% zeros. And so what was happening was I added some time delay in between switching between the thermocouples because they seemed to have to settle for a while before I would get a reading off of them. And so I could get that up to about 80%, but it was still not good. So this is kind of how the design all eventually ended up looking. I've got numbers now. I was really happy. I no longer had to use this as my temperature detection method. See my thumb there? It's pretty much back to normal now, but that whole stonemasonry thing. So yeah, lots and lots of baking. The bread is looking great because this is a retained heat oven. You burn inside the baking chamber and then sweep that all out, and then the bread goes in and bakes. And so you have to know how deep the heat is into the structure itself. And I've got these thermocouples at various depths, and so I can see how much heat I've got in there. So it doesn't matter if the oven is 400 degrees, if a foot into it, it's only 60 degrees, I don't have enough BTUs to cook bread. So it's been great. I do pizzas. My neighbor sometimes comes over and is my sous chef on pizza nights. Like Elliot, I spent the summer learning LVGL, and so this is the old setup, and this will be version 3 here. So a lot better understanding of where all these numbers actually are coming from. So. And then my next project is to build a rising cabinet, so this is going to be the display for that. It will heat up to 94 degrees, have high humidity, so it'll be a really stable environment to put the bread into time after time. So anyway, that's it.
Thank you very much. That's awesome. John Kunke, come on up. Find your slides. We are looking at John, then Mark, then Cedric, and then we are set. You actually want to stick around for all 3 of these?
So while he pulls it up, hi, my name's John. I generally do little electronic bits in my spare time. My main job is software. So when my wife finds some kind of project she wants to take off and do, she probably earns the term maker a little stronger than I do, but she tends to get a little bit off into the weeds and ends up going, hey, John, can you come help with a thing? And so this happened this year, and it's one of them was actually this shirt. We made family shirts for a big Disney vacation, and so she did the color blocking. I helped pin things together and get things cut out. So this presentations have a heart. Thank you for coming. Bit of a story, we were out, she saw that there was this haunted forest where a campground had decided to turn their stuff into a haunted walk you could do. So we went, and she was merciful to me, let me go during the kiddie walk, because I'm not a big horror fan. And for Seattle Lights, this is the haunted forest of Maple Valley. Next year, she volunteered. She says, "Hey, I can do some makeup stuff. I can do this." So she went and got into the system and started working with the organization. Then this year, she goes, "Hey, I'm going to go in right when they start planning for the year in like February or March." And she started end to end, and she started working on that. Oh, and I got us. Okay, so during planning, she had this idea. Actually, that's this. She wanted to take a whale fall and combine it with a lamprey eel and say, hey, what is this fascinating ecosystem that you find at the bottom of the ocean, and what if you got to walk through it in the creepiest manner possible? So everyone loved the rookie's ideas. Her first year doing everything, and says, you're not just in charge of your set, you get to be the first set in the whole walk, so everyone gets to see it first. Lots of pressure, lots of support. The volunteer organization built around this is fantastic. So this is the maw. This is what you see as you walk up to it at night. And you've got the teeth. You have this thing. You have to push past these giant cargo bladders. And so where's this heart? Well, okay, so over here you have the teeth, and you have to push back through. You come around, and around this corner in this kind of dark plywood hallway, you come along and see a heart. And we'll get to what it actually looks like in a second. So she took this thing from, the process is amazing. I can go through, there could be another talk on just her process of building this thing. But she could actually plow through, get it done, look ahead, get all this stuff executed. It was actually, originally, she was inspired by a video of a glass frog's heart beating. So this is a transparent animal, and you can watch the heart beat and the color changes that it goes through. She went from pipe cleaners to construction paper to sketches to watching videos on YouTube of different kinds of hearts, and then eventually built it up with chicken wire and armature wire. And we had some production assistants. This is Ray, this is Finn, and this is the heart hanging before they got the rest of the surrounding area done. You can see lots of the detail she got to put in. I will spare you that. If I get to the rest of the talk. So of course, it comes to me, what can I contribute aside from rubber ducking, occasional pair of hands, and the occasional tallness? LEDs. Welcome, we're at Hackaday Supercon. So unfortunately, we were kind of a week late, so we had like 3, maybe 4 weeks to get this thing done. There were other logistical nightmares, and so I said, okay, cheap off-the-shelf hardware. I have 3 weeks, and I need to start now. Okay, maybe plain off-the-shelf hardware, but we're just gonna go with off-the-shelf. I wanted to add a fruit. Fantastic hardware, great documentation, not cheap. Concept, 2-chamber heart, kind of 2 sides to things. Eels have more, humans have more, but okay, we can stick with things. We can pick some colors to make it nice and creepy. You can look up these transparent eels, which there's the glass frogs and the glass eels. I'm not sure what they're called, the eels were called. And so yes, we try to keep it familiar enough to be creepy, and so we stuck with a 2-beat heartbeat. And this is actually how I discovered freesound.org, which I can recommend. Thank you. ESP32, so bill of materials. ESP32, this nice little ASIC soundboard. It could drive 2 speakers. I said, you know, a few watts of sound for this little area, this should be plenty. This should work just really well. Cut a few strands of fairy lights. We actually doubled this at the last second. I was like, you know what? What if we just had 2 extra strands of LEDs? More LEDs isn't going to hurt anything. And they were, of course, coming from Amazon, quarter the price of the ones from Adafruit, but with a crappy no documentation to speak of, and yeah, that was an interesting experience. So then we got just a couple speakers here, and I was like, okay, we can put out 6 watts of audio. That'll probably do a good job. This is my prototyping process. I love pinning things to foam board, if you haven't bumped into that already. And then we got things zip tied to this nice piece. This is a floor mat. So because this was hanging up, and there's a possibility people could be under it, it had to be fire code compliant. So I'm dealing with this foam. This was the only piece. They had a nice rigid plastic we could use, but it was heavier than the entire sculpture. So we moved cruising right along. Software bill of materials, I picked up WLED. This is a really fun piece of software to start digging into and finding the different corners of what it can do. I've written a firmware like this for a different project before, just a manual LED thing. And it was nice to have someone else doing the heavy lifting, the event loops. But it also meant that some things like instrumenting different things to say, when does this start, when does this end, gets a little hairy. And I had to run into some interesting things like, okay, I have 2 strings of, ended up using all the LEDs. We needed all the LEDs, I could probably use some more. But if you're blinking 2 different segments in WLED and you need to keep them in sync, there's no facility in the software for doing this. The functions are a very stateless, oh, you have called me. Time has passed. I shall change color. There is no like, oh, I'm on beat 73 of measure 4. We're not doing that. So adding just 1 pixel to one segment was too much. The time difference between the scenes meant the two things got kept falling out of sync. And I also needed to get I had put this audio board in the bill. So I was trying to build this out and get people to get this audio effect along with this visual effect. And it turns out I just needed to pulse it. I ended up just kind of playing to my strengths. So I'm going to download the code and modify it and say, okay, well, when the heartbeat does this, we're going to blink the I/O and see how we can sync it up to. Oh, and I couldn't use audio reactive. You're sitting here going like, you're doing audio and LEDs, audio reactive, WLED, that's great. No, it doesn't work for this use case. If someone shrieks, the heartbeat gets out of sync, I'm sad. So then the sound was also a challenge because, yeah, when you're driving a $2 speaker at 20 hertz, it doesn't do anything. Oh no, you can feel it if you touch it, but it doesn't do much else. So tried a whole bunch of different things, adding another cone, that kind of worked. I wasn't brave enough to actually glue it to the cone and then try to squeeze it into this, into the heart with all the hard structures that we had to put up in there. Omnidirectional subwoofers were were just out of pocket. That wasn't gonna happen. Didn't have time at the line out adapters, so I couldn't just pull in a different amp and a different speaker. So really the thing is I had no time and no spares. If I'd been able to experiment with the speaker, I think I could have found something, but I gave up. So really, actually, I did have one solution that came up, which is I'm already editing the audio in Audacity to get it onto this little microcontroller. And so, hey, what if I just ran a little spectral analysis? Yeah, okay, all of the heartbeats have 90% of their power under 150 hertz, and the speaker has a data sheet. And so we get to, bottom frequency is 275 hertz. So some frequency shifting and some amplification and filtering later, it came out, okay, here's the entry to the final resting place with my lovely wife, and here is the heartbeat in its final resting place. And here are the production assistants one more time. Thank you so much.
All right, next up, I'm sure you have seen him around, Mark Marlin. He's been blinking for the past 2 days, 24/7. I have no idea what batteries he's got in there. I don't even know if we're going to learn this in this talk, but it looks like we're not. Oh, maybe we are. Well, let's see what happens. Ladies and gentlemen, Mark Marlin.
Hi. So this is a talk that didn't get submitted in time, so it had only 162 slides, and I had to shrink it down a little bit because apparently it's my fault if you're not eating right now. So we're down to 62 slides, which I think is 1 slide every 6 seconds. So yeah, I'm a computer guy because I did learn electronics earlier, but I was like, oh, it's hard, smoke. People tell you it's easy and it's fun, but you know, it's a bit more work when it doesn't work. The pi limit is not, it's a little bit high when things burn. You have to wait for new stuff, especially back in the days when you didn't have Amazon sending stuff in 1 hour or 1 day. High power also is no good. So after many years of not doing anything with electronics, I went to a Miniconf in Australia, which is where this badge comes from, and they're doing a similar thing than here, literally the same thing. And that's how I learned Arduino and a few more things. And I got this little guy, which only works if you blink its colors at the right time to actually mix your own colors. So I was like, wait, okay, so I have to write my code and all the stuff to make that work. So I made a driver for it. So now I have a full RGB driver for this guy, which actually incidentally happens to work just like the RGB panels that you've seen on me that you'll see later. Those things don't take a color. They take, are you blue on, are you blue off? And you keep making blue on and off very quickly. Same thing with red, same thing with green. And that's how you mix colors in real time by doing this millions of times per second. Then I got this, a little TFT, and that was first time we had this working on ESP32. There were no drivers at all, so I had to write all the drivers. I made an etch-a-sketch and a bunch of other games for it. Made a whole like small graphics library for it. And I'm going to skip to that because we really don't have the time. And of course, then NeoPixels happened. So by the way, I do not have an LED problem because I can stop whenever I want. I will consider it, but I'm doing just fine, thank you. So yeah, I got those and I was like, oh, but you can do matrices with them because I already had my little matrix from before. So I made matrix drivers for them. Then I made bigger ones. This is utterly stupid, by the way, making your own matrix by hand with soldering iron and glue. It takes forever. But hey, you know, it was nice, 24 demo. So again, I wrote a library to make a 2D matrix from that. Adafruit has some things on it, which was very nice. I was able to use that, but it didn't work well. The driver didn't work so well with the newer LEDs, so I used Fast LED and I wrote my own driver based on theirs on top of that. They also had, that was my first RGB panel, the one I mentioned, which is the same thing I'm wearing that has LEDs going on and off. There was a driver from Adafruit at the time, very limited, only worked on one size, and it worked on Uno, yes, the one with 2 kilobytes of RAM. So at the time, it was, you know, fun demos. So again, I wrote demos for it. Then I realized, hey, I need to have a graphics library that I can write against, so I can write my code against the library, and it will work on any backend. So those two that you're seeing, they're completely different hardware. They don't work anywhere the same, but with my library, I work against that, and then I have a driver underneath, and it makes stuff happen. So that was how I started. So yeah, then I went into, I've been doing EDM festivals for quite a while. I like to be lit up, but not this kind. Not alcohol is not the best for me. More of that, that's Burning Man. So I started with a lit up LED, LEDs on the shirt, nothing's too fancy, just not to get run over, and a few on my bike. Then I had colored LEDs that were all the same color because they were not addressable, and I wrote my controller for that and a bunch of stuff using a big LiPo. And I had different power systems. And then I started putting more LEDs on my pants and legs. That is, I believe, Dream States right here actually happening in a few weeks in Long Beach. And of course, I'm not the only one doing this, but I was trying to overachieve a little bit. It was fun to meet other people with fun stuff. I'm skipping a bunch of this because we don't have time, obviously. Then I made, oh, well, I should have NeoPixels on my shirt. At the time, it was difficult to do infrared and NeoPixels because of interrupts. Fast LED made things a bit better, so I learned all about interrupts, doing things in the middle of them. At the same time, I made a bigger matrix. So that was my first matrix that I was wearing using NeoPixels. And now I can do the shirt, which is a bunch of these. And when they go bad, you can still resolder them with the limited skill I have, which is not true of the newer ones. So that was the back of my panel. So this is the power issue. People ask me how many batteries you're carrying, and the answer is enough, but it's also a lot. Enough to make TSA people sometimes unhappy. They do not like LiPos, those green things on the side, because they say it looks just like plastic, you know, the explosive plastic. I say, well, no, we agreed it's not plastic. Is it okay? But by that point, they're pissed off, and I've already talked to 5 or 10 of them. I've been detained at several airports, including having the Army come once talk with me. So they don't like LiPos. They're completely fun and legal, but they don't like them. That's what I had at the time, because that's all the technology allowed. So that was my first shirt with a matrix. It was bright enough, and flexible. I was able to put it under the shirt, so that was kind of cool. So that was back, I don't know, 2018, I think. So that was, yeah, 2018, so EDC Vegas. So it was very nice, except, well, more pixels, more better, right? So had a bit of fun with that. Yeah, questions, we can do this later. So mission accomplished. If I were smart, I would have stopped there, but of course, I'm not known for being smart. So some person who hated me gave me 4,000 NeoPixels that he happened to have lying around, and he didn't want them anymore. So they looked like these, and I was like, well, okay, with 4,000, 496, that's a 64 matrix. So you just glue a few of them, put a few wires, and then you make a small. So you need a power supply to go with that. That's not based for batteries, obviously, because we're talking 160 amps. It's good for starting cars, though, if your car doesn't start. So that was the end of it. It literally took, I think, 10 days of laying out those strips one by one, solder every wire. It's absolutely utterly stupid. Do not do that. It went to Burning Man. It worked great. And then Burning Man ate all the pixels, and it burnt a bunch of them. That was very sad. Anyway, so that was now my first 64 matrix. This is what Burning Man does to your stuff. That part survived, by the way. It's the LEDs that did not. I met a few other people who had things too. Okay, moving on, because obviously this is an hour talk. So more pixels again. So now by that point I had to go to RGB panels. That's what you're seeing here. That's what I'm wearing. That's a 6464 that was on Teensy. Though this is a picture of the one I have with all the tape in the back, so you can see it's actually not that much anymore, just 3 panels on each side, some ribbon cables, a bit of power. There's a Raspberry Pi, and then a board to run 3 in parallel. The old version had the green plastic explosives, which definitely got me issues at airports. So I used to wear the batteries on the panels. I don't anymore because they every time wanted me to open it and take the batteries out to look at them. So the new one is now the batteries go down to a wire, which is USB power delivery. We saw the whole thing about USB. Now you can get 100 watts easily. Those panels are supposed to be 100 watts. You get about 75, 70 if you're lucky. So that's what I'm currently wearing when you ask me what batteries I have. So the answer is enough of those. My outfit currently runs with 2 of those in parallel, so I can run about 14 to 16 hours. And that is the end success. So now I can literally have high resolution, 128 to 192. I have a collection of over 100 DJs whose faces I have. I also made a few hats because why not? Then I had some company in China who sent me all the reject panels from Amazon because I became friends with them. So I have a bunch of free panels that I had to do something with. So I made a big display like these, and also did a few for my house. Nothing to do with the other ones. And in case you didn't get to see it, that's the one I'm wearing. I'll put the microphone down for a sec. When I dance, the sweat gets inside. It actually shorts the chips, as I found out. So the tape is for that, and also some people don't like to see stuff that has wires. They get kind of excited. So with tape, there's no wires. It's all black and nice. And it's slightly flexible. And there you go. Thanks for your time.
Thank you very much. Yeah, that was an hour talk in 7.5 minutes. Fantastic. And speaking of hour talks in 7.5 minutes, here comes Cedric Onet. Cedric's been doing a bunch of research in Shenzhen over the past year. This is going to be a year's worth of digging in 7 minutes. Or maybe 8.
Or maybe 20.
Nee.
Try plugging it in again. I'm not seeing on screen.
Oh yeah, look at that. Do you want to unplug, replug?
No, I think it might.
Oh yeah, you maybe turn it to external screen.
We have it set up to mirror the screen usually, if that's easier.
It's because I have.
Oh, you have speaker noise.
Speaker noise to go faster. It's not.
There you go. Yep. No. Yeah, you may have to mirror it. Sorry. Let's see. Oh yeah. No worries, no worries. We'll get there. Ta-da!
All right, thank you so much for being patient. I have about 370 slides. So that's about 1 second per slide. You have to be very focused. Do not blink, okay? No one blinks. If you blink, I see it. So, context reminder. Last year I was talking about this thing. It's a weird project. Who here is interested in strange manufacturing hacks? A few of you. Oh, all right. So, I've been making these weird fibers that I call, that have microcontrollers, sensors, feedback modalities, all sorts of things. I'm a PhD student, and to kind of justify why I'm doing these weird things, I have to look into the existing research. And I'm going to show you some really weird things that I found on the way. This is just to give an order of magnitude of what I'm working with. I need to go much smaller than that. So some of the applications, maybe some of you have seen, are some kind of wearables that are supposedly conformable. We basically make thin flex PCBs that are the shape of a fiber, and we weave them
make some all sorts of things. So there's 4 parts of this talk. It's about microfabrication and how can we scale this. So I think most of you have seen people doing weird soldering at the end of the alley. People have been miniaturizing a lot more than what is available here. Actually, I don't know. We'll see what happens today. There's some surprise. But this is just to give an order of magnitude. I went to visit the factory of Murata that makes those capacitors. This is the order of magnitude that we are looking at now. There's a lot of really cool slides that I can show about all the miniaturizations that we can put in these things. Basically, I won't go into all the details, but I'm playing with the semiconductors directly. And this is the kind of processors that I need to work with right now. It's way too big, right? I need more compression. So to look at all those weird fabrication processes, I looked at what is called heterogeneous integration. So people have been destroying phones and components and so on. Maybe some of you have heard of this thing called NeoPixel. There's, of course, there's a tiny processor. This one is about 0.4 millimeter. This is the kind of things that I need to work with. So you can put these weird integrations in accelerometers. There's all sorts of slides that I need to skip, or this one too. This has been explored since the 80s. People have been doing also the 3-dimension version since the 90s. And then around 25 years ago, people started to actually integrate with really high density in 3-dimension. You might have seen micro SD cards. This is what's happening inside. Many silicon wafers sliced and stacked. So this one has 8 layers. Now we're looking at 16 stacks. And there's plenty of slides that I have to skip. But this is really weird. These people have been putting battery, processing, memory, all sorts of things like that. So all of this is documented. And they make all sorts of various cool things, including wearables for butterflies. Because why not? Who wants a butterfly with a wearable? So this is the because it looks like you don't get it. This is the electronics that the butterfly is wearing. So people have been miniaturizing it even more. This is now 0.3 millimeter computer that has a very limited amount of computation and power. IBM has been doing it also. This is a kind of motherboard matrix. You can see 1 millimeter computers here. And I have all the specs. Ask me if you're interested. Now, once you have all those crazy, weird integrated circuits, how do you interconnect them? There's a couple of options. You can do it in a scalable way with this process called roll-to-roll fabrication. Photolithography has been an approach. There's plenty of HCI, human-computer interaction, people who have been exploring these for wearables. And I think for this audience, there's a cool hack that maybe some of you already use. You can buy now about $1,000 lasers that can engrave PCBs. So you buy a blank piece of copper PCB, and you can engrave it to make your PCB. That's interesting because it's more accurate than a classic PCB manufacturer, but it's also extremely fast. And there's all sorts of interesting publications that explain what's happening. There's a couple of things to look at. The wavelength that you will use for this will have a big impact. If it's infrared, which is the most common and the most affordable, you need a lot more power than if it's green or UV. And now there's UV lasers for about $5,000 that can do that. Again, I can share these details. I'll skip some of the details that I did, but there's one hack when you start to go in miniaturization, because my microcontroller is 1.4 millimeter, the pads underneath are 150 micron, and when you lace it, sometimes if your copper PCB is too thick, it starts to kind of fly around and make some shots. And to avoid these problems, you can use the thinner copper layer PCBs. So 9 micron, or I think it's a 1/4 ounce for those who use the system. Now, on the exotic approaches, these people have been, this is a PhD thesis, they've been using inverted electrolysis to clean up all the lasing. So when you cut traces with a laser, you get all sorts of nasty hair like that, and you can clean them with electrolysis, but the other way. So for example, if you want to make like a plated gold ring, you can take a piece of gold and then do the electrolysis. The gold will be kind of decomposed, and instead of using gold, you use your PCB or whatever you're trying to make. You can also use lasers to burn kapton and make conductive traces with this. So this is called laser-induced graphene, but it's actually mostly graphite. Now, if you want to play with this a little more, you can electrocute the thing with a 200-volt pulse for 20 milliseconds, and that will reorganize the carbon structure, and that actually makes something that looks more like graphene, not graphite. So in this case, I replicated it. You really get about 6 times better conductance. Okay, there's some weird micro-assembly techniques. I will skip a little bit. This is the coolest. People have been using lasers. This is called optical tweezers or optical traps. They've been using lasers to grab particles that are fairly small and move them around in 3D. And you can do that with micro gears for like biology, if you want to move red cells and things like that. But you can also use it for micro LEDs and like solder beads. So you can do pick and place with lasers. That's it. It's just weird. If you want to go even weirder, you can use a process called fluidic self-assembly, which is basically you take your PCB, thousands, millions of micro LEDs, you throw them in that weird liquid and shake them around, and they will go hopefully where you want. So this has been used stochastically, so it means you cross your fingers and hope that it works. But it's been used for high-density micro-LED pick and place. So they have all sorts of hacks that I will not go in details. They use like exotic magnetic fields and things like that. Now, the holy grail, can we make flexible semiconductors? And there's this patent that dates from 2007. People have been selling it. It's not high density. Now, because I'm making wearables, I'm looking at fibers, textiles, and so on. People have been looking at making the semiconductor directly on the fiber. This is the size that they're working with. I'm kind of sad that they did it before me. I don't think I would be able to do it, but yeah, still cool. Now, obviously, the hope is that eventually most of our electronics can become flexible. And this is a good hint, because these flexible screens are made with this semiconductor fabrication process. It's a different process, but it's a good hope. Now, what I'm working with, some of you have seen these, I'm making flex PCBs that are about 1.5 millimeter wide. I just came back from Shenzhen about 3 weeks ago and worked on this 0.5 millimeter wide version. And so this is a flex PCB, two-sided with LEDs on top and bottom. Sadly, I broke the connector, but I will try to fix it with a microscope here. And basically, the idea is that if you go back to this little processor, you can linearize them, make a long LED strip. That's cool. I have the chance to have access to wire bonding machines, so I can play with those tiny processors. And I can also show them. I have them in my backpack, if anyone is interested. And I take about 2 hours to solder one of them. It's like 14 soldering points. It's complicated process that I cannot go into details, but those manufacturers, they do it in about 1 second per LED. So there's a way to scale it. Now, you can go even higher density. Instead of using wire bonding, you can use what is called flip chip. So you take your bare die, actually you have to take the wafer, you pre-ball it, and then you put it upside down directly on the PCB, like if it was a normal SMD component. And we can do that with these LEDs, as mentioned, but what I want to do is, instead of just displaying information, we can still display, but we can also have electrodes, and these electrodes can emit a signal. And if you have some kind of interdigitated electrodes that are all connected to an analog input, you can scan the state of each of them and detect if you're touching or not using capacitive or resistive sensing. And if you're cheeky, you can electrocute the user with politely. So you can use a 400 micron transistor that would fit in that thing that I showed earlier. And that can work actually with 20 volts instead of the classic 200 volt, because you can go higher frequencies thanks to these scientists who found that our skin behaves a little bit like a resistor capacitor network. So higher frequencies go deeper in the skin. We can see it over there with the red. All right, so I went to hunt for bare dyes. This is the factory that makes those NeoPixel, World Semiconductors, and they gave me some samples that I can show. So this is a 0.4 millimeter wide, and so hopefully next year I will submit the talk and I will be able to show you this thing working. So scalability, I think, is an important part of what we are all doing, because we are hacking things in our garage, in our labs, in our kitchen, but many of our projects would actually be useful for other people. And I've been going to Shenzhen a lot, and I've been bringing friends with me, thanks to other people who did the same in the past, like Mitch Altman in Noisebridge, the hackerspace in San Francisco, and some others in the academic world at MIT. We've been also going a lot. And so I kind of took over this thing, and I'll skip all the cool hacks. You can basically get PCBs made in a few hours, because people have the lasers. They have shops that can fix phones, and they can do the assembly for you. You can go to the factory, see all your bugs. You can also forget about cloning, because what I call implicit open hardware is actually the norm there. Like, people just learn from each other. And if you really want to learn, you can also go to a shop, bring your PCB that you're curious about, and they can destroy it layer by layer and give you the files. Like, what is the design of this thing that you want to learn about? That's kind of how I would conclude. We are all somehow familiar with assembly and PCB design. And if you guys want to make your things at scale, please come to Shenzhen. This will be January 5 to 9 in the next January. Will be about 100 people on this kind of academic, but also kind of hacking tour, visiting factories, visiting electronic market, and so on. Thank you for your attention.